The internet is, simply put, a bunch of computers connected to each other. What started as the ARPANET in 1969 quickly grew into a large, rather gargantuan network that spans the entire globe. The main technology that made global communication possible is called, easily enough, the Internet Protocol. The Internet Protocol, more commonly referred to as IP, states that data must be transferred in packets or blocks of data. This is similar to how the post office does business. You must put your mail into an envelope that contains your destination and return address. Based on that information, the post office is able to deliver your mail virtually anywhere in the United States. IP is no different. An IP packet has its own source and destination address. Routers are then able to forward your packet to its destination. While you use your street address, city, state, and zip code to have your mail delivered, IP packets use 32 bits of information for addressing. This allows a maximum of 2 to the 32nd power of addresses to be used. Do the math, and it's about 4.3 billion addresses. That's a big number, but not when you compare it to the rest of the world. There are more people than IP addresses. Therein lies the problem with the current IP, which is known as IP version 4, or even shorter, IP4. As of 2007, there are about 6.5 billion people in the world, 1 billion of which use the internet. But then, more than one person can use multiple devices with internet access, and many more things might have internet access in the future. Obviously, desktop computers frequently use the internet for work, school, and play, and are most commonly found. People email each other for social and business purposes every day. Online games are becoming more and more popular. Schools are so integrated with computers that it would be nearly impossible to function without them. Did you also know many phones use the internet, as well as cell phones? They have IP addresses as well. What about cable TV? Even cars? That's right. Not only do GPS devices use the internet to access their information, new technology will probably allow your car to contact the shop if there's an oil leak, automatically. If that's the case, then why not your refrigerator? Your water heater? Your microwave? You see, the internet and its applications are growing exponentially. Every electronic device on the planet can potentially have its own IP address. Though some techniques, such as network address translation, NAT for short, have kept a limited pool of IP addresses from going dry, it won't last forever. This is why the next generation of the Internet Protocol, IP version 6, is soon to be implemented across the globe. The main feature of IP version 6 is that instead of using 32 bits for address space, 128 bits are used, quadrupling the amount of data dedicated for an address. This allows a maximum of 2 to the 128th power of addresses, or roughly 340 trillion addresses. Here's the exact number. Big, right? This astronomical increase, and I mean literally astronomical increase in addresses, is expected to last the world a long time. IP addressing space is so big, in fact, that it is simply impossible to show it to scale. Imagine for a moment that a 1.6-inch square can contain all of the current IP version 4 addresses in space. In that case, the IP version 6 address space would be represented by a square the size of the solar system. It's pretty difficult to grasp how incredibly large this number is. So here's another example. The Earth is about 4.5 billion years old. If we have been assigning IP version 6 addresses at a rate of 1 billion per second since the Earth was formed, we would have by now used up less than 1 trillionth of the address space. Needless to say, IP version 6 is projected to allow plenty of unique addresses for quite a while. However, how can we expect the world to migrate over to a different version of IP? Billions of users access the internet, and worldwide commerce is dependent upon the internet working 24/7. The goal of a reliable network is to be up 99.999% of the time. That's not a forgiving standard. Changes need to be implemented seamlessly, with no disruption for the user. Currently, there are solutions being put into place for the transition between IP version 4 and IP version 6. Since it is impossible to just update every router and host on the planet simultaneously, changes need to be made in stages. The user isn't even supposed to know that a change has ever occurred. To ease into IP version 6, engineers need to be extremely careful. One such change is being done on the software side, called dual stack. Dual IP version 4 and IP version 6 stacks simply mean that a single computer has both versions of the Internet Protocol working at the same time alongside each other. An email server, for example, will be able to provide its service to an IP version 6 host and an IP version 4 host simultaneously. This enables gradual, one-by-one, step-by-step upgrades to applications while still allowing older applications to work just fine. Operating systems on individual PCs and Macs have supported IP version 6 for years now. The potential is already there for application writers. The only problem has been getting the applications to make use of these features. Routers themselves need to be configured to route IP version 6 traffic. Cisco has made this task exceedingly simple. They added an IP version 6 command set to both their global and interface configuration modes. All basic router functions are compliant with IP version 6. RIP, IGRP, EIGRP, OSPF, NAT, DHCP, ACLs, and DNS are all IP version 6 compliant. Switches don't even need to be changed, since they operate at layer 2 and are thus oblivious to the network protocol in use. Routers that support IP version 6 are limited to large enterprise routers like the 7600 series, but IP version 6 functionality for small home and business routers like 2900 series is not very far away. Until then, how do you make use of all the IP version 6 goodies out there if you're in an IP version 4 network? A vast ocean of IP version 4 infrastructure stands in your way. This is where tunneling comes into play. Though there are several tunneling techniques in place, they have one key element in common. IP version 6 packets are essentially smuggled inside of IP version 4 packets until they reach the IP version 4 internet, in which they can strip off their IP version 4 shell and continue on their way. That way, the IP version 4 network will have no idea that a change has ever occurred. All that is needed is a border router that can either translate or encapsulate IP version 6 packets for its journey. What about the other way around? What if an IP version 6 host needs access to an IP version 4 service? In that case, an IP version 6 packet is completely translated into an IP version 4 packet to be used by the server. On the packet's way back, it is then translated into its original IP version 6 form. Dual stacking and tunneling are ways to temporarily allow IP version 6 functionality before a network can be upgraded to fully support IP version 6. With these techniques in place, the internet can continue to grow and expand, allowing more and more users to access more and more information every day.